I'd like to state we are very impressed with this mock-up. Block 2 is about as different from Block 1 as Block 1 was from Gemini. There's quite a difference in the two vehicles.
Block 2 is the basic manned Apollo configuration. This is Captain Shira, mission commander of the first manned flight. He is speaking at a press conference at North American Aviation, 1 month and 10 days after the 204 accident board ended its investigation.
To attain the confidence that we need again to fly a manned spacecraft.
It made 8 recommendations directly concerned with the spacecraft. How effectively does the first crew believe those recommendations were carried out? Where do we stand in the overall manned spaceflight program? With Captain Shira, a veteran of both Mercury and Gemini, will be 2 young astronauts making their first manned flight. Don Isley, command module pilot, center couch, and Walt Cunningham, lunar module pilot, right couch. We have kept standard Apollo crew designations for the first manned flight. But without a lunar module, we have to make some changes in crew responsibilities. Of course, the mission commander bears full crew responsibility on this and all Apollo flights. However, the command module pilot now becomes the guidance and navigation expert. He will also handle any rendezvous procedures included in the mission. Since there is no lunar module, the right couch pilot, Walt Cunningham, will be the expert on all spacecraft systems.
I think it's appropriate that we at least identify some of these changes to you that are in this mock-up. I'd like now to have demonstrated to you by Don Isley, who is our center couch man, demonstrate the hatch itself.
I'd like to call attention to the new hatch design. We now have a hatch which is hinged to the spacecraft, and it seals on the outside rather than from the inside. When the hatch is closed, these dogs go over center and pull the hatch down against the outer seal and form a seal. That way, if there is any pressure buildup inside and you had to get the hatch open in a hurry, there's a quick release device which pulls these dogs back and lets the hatch swing open very quickly. It's very similar to the Gemini hatch design, and we find this is much superior to operationally, and it's also a lot safer than the old design, which was sealed from the inside with hatch panels that had to be installed from the interior.
We can open the hatch, I'd say, within 2 or 3 seconds. Now, getting all 3 men out is the timeline, and that's the kind of thing that we practice.
Captain Shira, what kind of timeline are you looking at for getting the crew out of the spacecraft, including hatch opening and egress?
I'd say we could, with the help of the external crew, get out in 15 or 25 seconds. I would rather not be pinned down on the time until we train and practice emergency egress.
In addition to the hatch design, major changes have been made in the spacecraft interior. The wiring, electronic boxes, and plumbing runs are covered by protective panels. Stowage space is used more economically, and all flammable materials such as paper checklists, meteorite garments, even tissue containers are now stowed in hard metal containers.
Tom Stafford, mission commander of the backup crew, a crew familiar to us from Gemini. Stafford made his first flight with Captain Shira, and later was command pilot of Gemini 9A with Gene Cernan, now his lunar module pilot. John Young, command module pilot, is another space veteran. He made his first flight on the first manned Gemini and was also command pilot of Gemini 10. In all, the 2 Apollo crews represent more than 275 hours of manned space flight.
To now let Walt Cunningham have the same privilege I did.
All the wire runs that used to be exposed are now enclosed under metal covers. They will protect the wiring from damage and isolate the whole wiring system from the wear and tear of people getting in and out of the spacecraft. These covers also form a good fire break. These flat boxes are stowage containers. They are all hardcover, rigid metal boxes. Anything that is flammable, or really, anything that is flammable for which we do not find a good substitute material, will be enclosed in these protective cases.
The fire, as we can best determine, was caused by a wiring malfunction. This was a trigger which ignited the combustible materials in the spacecraft, and they burned very rapidly. Those materials have been almost completely removed. We have a very large list of substitute materials that are being developed daily to replace them. Some obviously flammable materials remain. They include, of course, the 3 crewmen themselves, and they eat food that is combustible. As a result, the food and the crew will be packaged more carefully. The suit we will be wearing will not be flammable. So if we remove all the triggers that we can possibly remove, and if we remove all the combustibles that we possibly can, and encase the combustibles that we must have in non-flammable material, there should be no cause for anything to burn, even in a pure oxygen environment.
We have retained the 100% oxygen environment as a basic life support system for Apollo. The spacecraft will be purged to a 5 psi level in orbit. However, we have added the capability of employing a 2-gas system on the launch pad if it should seem feasible at a later time.
The spacecraft has gone through some changes in systems as well. One of the changes in the systems is to accommodate the spacecraft to be launched with air or nitrogen and then purged in orbit to have a pure oxygen environment. Now in orbit, this would be approximately a 5 psi oxygen environment, not 16 to 19 psi as we see on the launch pad. And there is a tremendous difference in the flammability characteristics of materials at this lower pressure.
Question here.
Can you relate the complexity and the preparations for this mission to the complexity and preparations for Gemini and Mercury?
Training for the first flight is about 2.5 times as complex as it was for some of the latter phases of the Gemini missions. Training-wise, I think the crew will be in good shape. For example, I think we're going to be a lot better for this first Apollo flight than Gus and I were, getting ready for Gemini 3, the first manned Gemini, because there will be more simulators available.
The Flight Crew Support Division, MSC, has 3 Apollo simulators at the Kennedy Space Center and 7 at the Manned Spacecraft Center. Where Gemini required 1 basic mission simulator, Apollo needs 2 separate pieces of hardware to simulate a complete mission, the Lunar Module simulator and the Command Module simulator. This follows from the 2 spacecraft phases of the mission. The Command Module simulator realistically duplicates flight hardware. The crew area contains active controls, switches, and instruments. It also presents visual displays through the spacecraft window of the Lunar Module, Earth scenes, lunar scenes, star fields, and so forth. Looking at the simulator from the outside, the displays bulk very large, and sometimes the astronauts call them the boxcars. A digital computer complex programs the simulation. An instructor directs crew training at a console, which duplicates the instruments and displays of the Command Module simulator. The instructor can insert given mission phases from his station and repeat that phase immediately for review training should he or the crew feel this would be desirable. The Lunar Module simulator, which fills in mission phases unavailable in the Command Module simulator, follows a like pattern. There is the simulator itself and displays such as star scenes and lunar surface scenes. It is also furnished with an instructor's console, computer, and equipment racks. To the left of the simulator is a three-dimensional mosaic of the moon surface. Through closed-circuit television, it presents typical lunar landing displays marked by craters, mounds, and boulders. The mosaic gives the astronaut a realistic feel for his final landing approach. Lunar module motion is simulated by moving the map up and down for vertical motion. A camera on a dolly track provides lateral movement. Lights around the camera lens simulate lunar lighting conditions. With these two simulators, a crew can practice the basic flight elements of the Apollo mission from launch complex to landing on the moon and return to Earth. For more detailed training of critical phases, the astronaut turns to specialized simulators. Let us look at some of them. Wherever possible, these have been modified from existing Gemini hardware. The Dynamic Crew Procedure Simulator, which stresses launch and launch abort training, was converted from Gemini. It provides a physical environment such as motion, sound, and the onset of gravity so that the crew can evaluate launch vehicle performance.
6, 5, 4, 3, 2, ignition. Liftoff. Apollo 7, be advised you have pressurization problems in the J2. Stand by for possible abort situation.
Roger, standing by.
Roger, pressure still decreasing. Apollo 7, decision is to have you abort at staging, so I will give you a countdown. 3, 2, 1, abort.
With such training, Captain Shira was able to react immediately to the shutdown of Gemini 6 on the launch pad. This is the old target and docking simulator as used by Gemini crews.
Range, if you're ready, I'll reset.
It has undergone a facelifting, substituting the Apollo Command Module and Lunar Module stations for the Gemini and the Agena target vehicle.
At this point, you should slow your closing velocity to approximately 1/10 to 3/10 of a foot per second.
Okay, is this the recommended docking velocity?
That's correct. Okay, I have indications of all latches. The probe should be retracting.
Okay, it seems to be.
Okay, that's it. And then you can back it on out again.
Okay, fine.
Okay, I'm releasing.
All right.
In your in conditions, you had a 90-degree pitch down, a degree yaw right, 0 roll. You're offset a little to the left laterally. That's probably why you had the yaw right in there. You're lined up vertically. Contact velocity is 1/10 of a foot per second.
Okay, fine.
EVA training centers around two complementary simulators, the Water Immersion Facility and POGO, a partial gravity simulator. The value of underwater training as realistic simulation of weightlessness for study of space tasks was borne out by Buzz Aldrin during Gemini 12 EVA. This experience is being applied to the lunar mission and to the space workshop. But the astronaut on the moon will work under 1/6 Earth gravity, setting up scientific experiments and gathering geologic samples. POGO simulates both 0G and 1/6 gravity conditions. For lunar work simulations, a pneumatic tube counterbalances 5/6 of the astronaut's weight. Gemini crews had the use of two mission simulators, one at Kennedy Space Center, one at MSC. These have been combined into a single Apollo Procedures Development Simulator. It has two crew stations, one command module, one lunar module. In them, the astronaut can practice specific flight elements of the mission, such as thrust maneuvers, star sighting, and so forth. However, the sheer number and complexity of Apollo simulators and related equipment has strained existing facilities. Ground was broken in February on a new flight crew support building to be completed in 12 months. It will house the Procedures Development Simulator with a new computer complex to increase the depth of training. But this is looking a little to the future. For the present, all simulators needed to support the first manned Apollo mission are man-rated and operational. The slow details, the hundreds of hours of simulator training, have begun. Progress in Apollo support was exhibited by the Real-Time Computer Complex, RTCC. The older 7094 computer, which supported Gemini ably, had reached the end of its growth potential. It had been modified to the fullest extent and was operating at capacity. The RTCC has replaced all 7094s with 5 IBM 360s Model 75J computers. In addition, another Model 75 computer is housed in Building 422. It generates simulated network data used in mission training exercises. Apollo now has a computer with 3 to 4 times the internal speed of the 7094. The Model 75 is modular in form and open-ended for growth. Among other advantages to the conversion is the fact that the Model 75 has more checking circuits than were available on the 7094s. Despite the increased speed, growth potential, and capacity, rental is cheaper than the 7094s. We should also look for a moment at the Communications, Command, and Telemetry System, abbreviated phonetically to CCATS. It is composed of 3 UNIVAC 494 computers, 2 used online for mission support, 1 for program development. Through this system, the RTCC receives all mission data except voice, teletype, and some AeroMed data. It is fed into a UNIVAC 494, and from there to the 2 Model 75 computers supporting the mission. In addition to this function, retained from Gemini, CCATS now replaces the Master Digital Command System in sending out mission commands. Let us say that the flight director at Mission Control Center wishes to send a command to the spacecraft onboard computer. The information goes from his console to CCATS, which encodes the message. It is sent to Goddard Space Flight Center, which transmits the information to a remote site in contact with the spacecraft. For this example, let us say Hawaii. And from there, it is sent by radio signal to the onboard computer. With the older system, we could only command 1 site at a time, which meant commanding only 1 spacecraft, manned or unmanned. With CCATS, we can command 4 sites simultaneously. Beneath the smooth tile floors and corridors of Building 30 stretches a network of more than 195 million feet of wiring, enough to go around the Earth 1.5 times. Wiring for computers that can perform an addition in 0.8 of a billionth of a second. Computers which can receive telemetry or trajectory information from Goddard, check it, and display it on a flight director's console in 1 second. When we set up scientific experiments during the lunar mission, we will have the information displayed in mission control 4 or 5 seconds after it is sent. In this one room is the greatest computer capacity in the free world. 7 days before the end of the report period, the Lunar Receiving Laboratory was opened. The newest facility at MSC contains 83,000 square feet. It is divided into 3 areas. There is a crew reception area for isolation and study of the Apollo crew immediately after the mission. It supplies necessary housekeeping facilities, living quarters, and medical facilities for crew examination. Sample operations provides for preliminary investigation of lunar samples, including physical chemical tests, gas analysis, and radiation counting. Both these areas are in quarantine isolation. The third area, support and administration, is outside of isolation. It supplies conference rooms, office space, and support activities such as biological support laboratories. Quarantine actually begins far from this laboratory. It begins when the crew leaves the moon surface with 40 to 50 pounds of lunar samples vacuum sealed in a special container. It continues unbroken by means of a mobile quarantine laboratory, which the crew and samples will enter on shipboard direct from their returning spacecraft. The sealed spacecraft will also be brought to the Lunar Receiving Lab and housed in this room, which is normally opened to the outside. If the spacecraft must be entered for any reason, the outside doors will be sealed and the room will become part of the crew reception area. Lunar samples must be protected against Earth contamination, and the crew will be observed by doctors for the remote possibility of lunar contamination. Quarantine period for crew, 3 weeks. For samples, 4 weeks. Quarantine continues at the Lunar Receiving Lab by means of primary and backup systems of containment. A biological barrier is provided by special filters on air conditioning systems and by airlocks irradiated with ultraviolet light, by special sealing of floors and walls, and by sample cabinets, and by other means. 50 feet below the ground is a radiation laboratory, part of the sample operations area. As soon as possible, a radiation count will be made of the samples to assure us that very short-lived isotopes are identified and not lost. The laboratory is put underground to shield out cosmic radiation. Extreme care is taken to obtain a true count of activity of the samples. For example, radon, a radioactive gas, is present in the atmosphere in minute quantities. It will be filtered out by the air conditioning system. Walls of the counting room are 8 feet thick, 5 feet cement, 3 feet dunite. Dunite is a natural mineral rock which is an effective radiation barrier. Using it, we avoid the cost and weight penalties of lead shielding. The biological support laboratories in the support and administration complex are raising plants and animals to be used in tests of different media for possible lunar viruses. Cultures will be prepared in the support laboratories, sterilized, and sent within the quarantine barrier of sample operations for testing. In studying these cultures, the electron microscope gives us the possibility of direct visualization of virus material. Preliminary analyses will also be made to classify and catalog the samples at the laboratory and to identify the elements present. As soon as possible, the samples will be distributed to scientists for study in their own laboratories. Distinguished scientists will concentrate in their specialty areas. Studies will continue for years. Participating will be scientists from countries all over the free world. They will share with us an experience unique in man's history, first-hand study of the composition of the moon. We have reviewed the most active 6 months in the history of the Manned Spacecraft Center. It required total effort to recover from the late days of January and move forward with the Apollo mission. For the first manned flight, the spacecraft has incorporated the recommendations of the 204 board. The first crew is in training and has the simulators to do the job. Mission Control is ready to support upcoming Apollo missions with new computers and new capabilities. We are looking ahead and preparing for the day when the crew will return from space and bring to the Lunar Receiving Laboratory part of the moon.